Hello, I'm Emre. I work for SYBO as a game engineer, and today I have a very bold topic to talk about, which is OOP's Obsolete. But first, I'm gonna start with introducing SYBO to you. We are founded in 2010. We have over 154 employees and over 40 nationalities. We have an internal joke that's saying, if you blindly throw a dart at the map, you will probably end up where a Cybonian lives. So, a bit more about me, my social links, if you want to get in touch with me. We recently reached the 4 billion downloads worldwide. We are available globally, and we are running this game almost for 11 years now, even though we have still over 25 million daily active players. Who played Subway Surfers here? Almost all of you, as I guessed. And we are the most downloaded game of the decade in mobile. So let's begin with our topic now. What is OOP? For non-technical stuff, I'm sorry for you. It stands for Object-Oriented Programming, which is somewhat industry standard now. And it aims to solve the programming problems in a real-world analogy approach. So, for example, if you're going to introduce a dog to your game, you're going to introduce a dog class first, and you populate that with some logic and with some data, and there you have it, your dog. And it's based on the real-world analogy of the dog. But there are many problems with OOP. For example, it tries to solve the wrong problem. As a developer, as an engineer, your purpose is not to solve the real-world analogy problem or make it understandable to humans, but make it as efficient as possible for the computer. So that's firstly wrong. And the tool becomes the purpose at some point. Because there are so many OOP principles, so-called principles, that you should consider, you sometimes forget what to solve here. You try to solve OOP's problems, which is very, very wrong. And there is also the infamous diamond problem, where you can do a multiple inheritance and doom your code base. So, what's the solution, Emre? What are we going to do? I introduce you with DoD, which some of you probably already using it, but who doesn't, here it is. DoD stands for Data-Oriented Design, and it aims to solve the problems in the most efficient way for your hardware, which actually, in this way, you get a lot of performance benefits, which can contribute to your tech KPIs and basically everything. Because if you have a strong code base, if you have a strong tech KPI, you can set to do anything, basically. So, one of our first comparisons here, composition over inheritance. So as you know, OOP actually encourages inheritance, which is very, very bad because it's statically behaviored, not dynamically. And there are some couple of caveats here, which I'm going to talk about now. As first, static versus dynamic behavior. So inheritance is actually statically typed in the compile time. You can't change an inheritance after the compile time, basically. You can't do that when your game's already running. But if you are using composition, you can do that. But what is composition compared to inheritance? So you probably already know what inheritance is. For example, in your game, you have 2 vehicles. One is tractor and one is truck, and they both derive from the vehicle class. But let's say you want your tractor to become a destructible object. So you can do 2 things in the object-oriented way. One is to make the whole vehicle class, which is the parent class for both of them, a destructible object. But wait, I just want the tractor to be destroyed, not the truck. Okay then, polymorphism, right? You just slap an interface there, make it destructible? No. That makes your code unreusable. You have to do another implementation of a destructible object whenever you implement an interface there, basically, which is very, very wrong. It limits your code reuse. Guys, please. But let's say we are doing that on the composition way, which is data-oriented way, by the way. There's our tractor. You slap your destructible component there, and bam, now it can be destroyed. Because you just tag it, basically. You just say, now that's destructible, and now, okay, that's destructible. And as you see, it behaves dynamically. I just changed that in the runtime, not in compile time, which makes your code base very, very flexible. Unit testing. I know in hyper-casual genre, you don't do a lot of unit tests, but if you are doing in some way, you're probably came across with mocking problems. For example, if you are using OOP and inheritance a lot of places, you can't just mock abstract classes, right? You can't just mock their implementations, you can just mock their anything, basically. But if you are using composition, you can mock virtually anything. Virtually anything. You can mock the data, you can mock the behavior, you can mock anything you want. And encapsulation. So-called OOP principles, one of is actually the encapsulation. So encapsulation is actually protecting the behavior of your classes, of your data, and blah, blah, blah. So, but if you take a look at this diagram, so for example, we have the engine component here, and let's assume that the engine is a property of the vehicle. So both track and tractor will have an engine component, and because it's derived from the vehicle class, right? But I want them both to behave differently, which will break encapsulation when you think about it. And in multiple layered inheritances, this problem can get worse. For example, you can break the parent's class behavior. You can break many things when you think about it. But if you are doing the data-oriented way, which is composition, again, you don't break anything. You don't break any encapsulation. Not on your systems, not on your components, not on your objects. And this brings us with some also performance benefits, like I said, because of how you lay out your data in your memory, which is very, very important for your hardware to work efficiently. So, as you see, this is an example of a modern CPU. You have the CPU right there. You have some caches, which I'm going to talk about right away, and you have the RAM and blah, blah, blah. So, what are those caches? So whenever you want to receive a data from your memory, whenever you want to read it, you actually don't only get the address you want to. For example, this green X right here. There is something called data locality, and your CPU assumes that you're also going to use the contiguous memory data in the next couple of addresses, and it's going to just fetch those addresses to its cache. So if you look at the array of structures here, which is the OOP way, by the way, it's pretty much disorganized and chaotic. So if I want to read from the YX address, the CPU is going to cache the YRED address, and then when I try to use it, it's not going to do anything, basically. Because this is completely a different object. It's completely a different data. But what if it's being used from the CPU? So let me explain something to you here. These caches you see, these caches are so fast, but yet so small. So approximately, I think it's like 8 kilobytes or 16 kilobytes. I can't remember right now. But they are so small, but they are so efficient and fast, much faster than the main memory. So when something is cached, And if you get a cache hit, which means that you are using a data which is cached, your program will run much faster because you're basically reading much, much faster from the main memory. But array of structures, which is the OOP way, can't provide you with that because of how you lay out your memory in the RAM. Let's take a look at the data-oriented way then, the structure of arrays. So as you see, the memory is contiguous. It's pretty organized. So every every green X type of data is laid out contiguously, which allows you to use the cache. So for example, if I want the first green X right there, the other X's would be cached into those L1, L2, and L3 caches. And then when I want to use the next green X, it will just be provided from the cache and not from the slow-ass main memory. So, but that's just talk, right? I'm just talking here, just theoretically. How about some practice? So, I boosted up my Unity, which I'm guessing most of you guys are using, and create an example scene here. So first, I did the OOP way. I created 2,048 balls in my scene, then attached them with some kind of ball component, which is the OOP way of you doing this. And what did I do? I just moved them 1 unit per frame, which is a very, very basic action. What did I get statistically? 45 FPS, 2,048 calls, and the time it took was 1 milliseconds, 0.39, yeah, which is insane, actually. Look at the call size. But what if I did this with DoD? I showed you all the performance benefits. I showed you every argument I had. But let's see in practice, right? So again, same scenario. I have 2,048 spheres. They are moving 1 unit per frame, blah, blah, blah. And what I get is 114 FPS in a bad day, because this is not pure. This is just Unity's transformation. This is not pure. Like I said, it's a bad day for the DoD. And only 1 call, and time it took was 0.33, guys. Come on. And this is the thing. As you see, I laid out the transform classes contiguously on my memory and iterated over them, and basically doing the same thing. So yeah, the performance benefits are real, just not theory. And this will, I guarantee you, this is going to impact your tech KPIs really, really well if you are using it. So you should better start using it. And thank you. Thank you for listening. I appreciate all of you here. That's it from me. If you have any questions, you can reach out to me from anywhere in here or anywhere else you would like to.